Welcome to this Physical Review Fluid Journal Club, the first of this new year. My name is Guido Boffetta from the University of Torino in Italy, and I will be the moderator for today. So the talk of today is based on an editorial suggestion paper published in Physical Review Fluids in November. And the paper is by Chunlai Wu from the Eindhoven University of Technology, together with Rudi Kuhner, Ziki Wang, Sander De Witt, Federico Toschi, and Herman Klerks. And the title is Tracking the Rotation of Light Magnetic Particles in Turbulence. So the talk is going to be for roughly 15 minutes. We will not take any question during the talk, so please mute yourself. And then if you have any question, you can post on the chat during the talk, or once the talk is over, we will have another 15 minutes roughly for discussion, when you can simply raise your electronic hands and ask questions. Okay, so Chulai, please, you can start with your talk.
Okay, thank you so much for the introduction. It's my great pleasure to be invited to this journal club. And of course, this is a great chance for me to introduce our work to a wider audience. So let me get started. This study is basically to introduce a new experimental platform that we have developed to do some research on particle-laden turbulence. So in this talk, I will firstly talk about the design of our experimental setup and then how we built our optical systems. And then I will talk about our magnetic particles, how they are made, what their main features are. And then after that, I will briefly explain how we do the rotation tracking for our particles and then the corresponding image processing. And finally, I will show you some results from the real experiments. But well, before going into the setup, I would like to explain where this the idea of our project comes from. So it starts from a very common phenomenon in turbulence, which is called the preferential concentration. So when we put particles with different densities into a fluid, say water, heavy particles tend to move toward regions with high strain rates, which means they are pushed out of vortices. But on the other hand, when particles are lighter than water, they will be trapped inside the vortices because of the pressure gradient. This is what you can see on the right side of the figure. The black arrows show the velocity field, and most particles represented by the red spheres, they stay inside the swirling structure. So a natural question would be, can we just use these light particles to interact with turbulence? For example, what would happen if we force those particles to spin using an external field? The first and most basic question then would be, how can we study their rotational dynamics? And this is exactly what I will focus on in this talk. So to study this, we designed this new experimental setup, and at the center is a turbulence generator, which is also called the French washing machine. It has two counter-rotating impellers, one on top, one on the bottom. When they rotate together, there will be a homogeneous turbulence generated in the center of the water tank. And around this octagonal prism water tank, we also have two pairs of perpendicular Helmholtz coils generating a rotating magnetic field. And in this figure, this magnetic field is rotating in the XY plane. And then to record the rotation of those particles, we need only one camera. And of course, we prefer to align this camera with the rotating axis of the particles, which is also the rotating axis of the magnetic field. And then we also need two LEDs on both sides of the camera at 45 degrees, which are indicated on the right. So there's a photo of the setup on the left. I also put some numbers about the dimensions of the setup and also about the turbulence we usually use. So actually, it's not a very big setup compared with the high-speed camera on the table. On the right, this is a time-lapsed photo from the raw recording of the camera. We can see that there are only actually four particles that are nicely in focus so that they can be selected as candidates for afterwards rotation tracking. So as I mentioned, there is only one camera needed. the key point here is that every particle has unique and different surface pattern. And advantage is that we do not need to predefine or do any pre-designing for the surface pattern on those particles. So how do we do this rotation tracking? We actually use an algorithm developed by another group in Zurich, which has already widely used in capillary flows, but now we apply it to turbulence. This algorithm applies only for spherical particles. It uses only 2D images to fully recover 3D rotation by projecting those 2D surface pattern back to a virtual hemisphere and then calculate the cross correlation peak between each two consecutive frames. And then because we already know the frame rate of the camera, we can immediately have the angular velocity of each single particle in the flow. But unlike those standardized surface patterns shown on the left, in our experiments, the particles we use, they are actually made of styrofoam particles. We just simply buy some styrofoam particles from website, and then they are originally white, and then we cover them with magnetic paint, which is in some kind of dark, like purple color. Together with the original white color of the styrofoam particle as the core part, we have this kind of surface pattern. But because everything of this fabrication is done manually, so this coating is non-uniform, and then the surface pattern of each particle is unique and different. So those particles are around 800 microns in diameter, and they are all 80% lighter than water. And they all have anisotropic magnetism, which is from the non-uniform magnetic painting and also their shape imperfections. But it is exactly this magnetic anisotropy that allow those particles to follow the rotation of the external rotating magnetic field. So then we have to do the test to test if this tracking algorithm works well on our particles. So we just simply put some particles in still water. There's no turbulence at all. And then we turn on the rotating magnetic field, which is 1.6 millitesla, 20 hertz. And then some particles, we can see some particles are rotating, some particles just oscillating due to the different, slightly larger local friction. But it's not the point here. So I put the tracking results on the right. For particle one, we can see that only the Z component, which is the green line, that is aligned with the direction of the rotating magnetic field, is going up and down, which is indicating that this particle is oscillating in this direction. And the other two components, they are just staying around zero, which totally makes sense, which means this particle is not rotating in these two directions. And for particle two and particle three, we can see that only this, again, the green line, which is the normalized angular velocity, which is aligned with the rotating vector of the magnetic field, stays around one, which means those two particles are really exactly following the rotation of the magnetic field. So we can say this confirms that our tracking algorithm works pretty well on our particles. And then in general, I need to briefly explain how we extract each single particle's rotation from the very raw images, from the very raw recordings of the camera. So first of all, we need to locate every particle, and then track everyone over time. This is just a simple 2D tracking on 2D images. And then we need to crop each single particle into a very small size. So the original image is like 1024 by 1024, and then each cropped single particle image is only like 100 pixel by 100 pixel. And then we get rid of those blurry particles, only keep those very nicely in focus particles, and then feed those images to the rotation tracking algorithm. Then we finally get those particles' angular velocities. So we can go to the real experiments. First of all, there is only turbulence. There is no magnetic field. We can see that those particles just randomly moving around. They seldom rotate. They just sometimes shake. And then once we turn on the magnetic field, we can see, oh, most of those particles really immediately start to rotate in the same direction, basically. So this direction must be the direction of the magnetic field rotating. Yeah, so Here I put some PDFs of the angular velocities from the tracking algorithm. Um, sorry. On the left, again, there is no magnetic field, only turbulence. So I plotted all three components of the angular velocities. They're all pretty much the same, and they have wide tails indicating the intermittency of turbulence. So this is already good enough to say that our results make sense physically. On the right, I put only the component Z here, with magnetic field frequencies ranging from 5 Hertz to 40 Hertz, but with also the case with no magnetic field included here on the very top. So we can see in every PDF curve, there is a peak following the increasing magnetic field frequency from 0 to 40 from left to right. But this peak is also shifting downwards, which means there are less and less magnetic particles can follow the rotation of faster magnetic field rotation. Or maybe even those particles can follow the rotation with faster frequencies. They can only follow this rotation with shorter and shorter duration. So I will not go into details about the rotation dynamics here, but I would say so far we can already say this newly developed experimental platform is performing very well. So since we have the rotation tracked, of course, we would like to integrate Lagrange particle tracking into this system. We have already tested all the hardware. Now we can see that we have already three high-speed cameras with two green LEDs put against each other to illuminate the volume in the center. Everything is going well. Data collection is ongoing, but that'll be our next story. So, okay, to summarize, we have developed an experimental platform to track the 3D rotation of light magnetic particles in turbulent flows. And next, we will integrate Lagrange particle tracking to simultaneously track their translational and rotational motion. That will help us to have a better understanding in the interaction between particle and the turbulence. And then we will also investigate the back influence of particles on turbulence at higher concentrations, like 1%, 3%, even 5%, with some global large-scale measurements like torque measurements. Yeah, so that's pretty much it. Thank you again for your attention.
Thank you very much, Chunlai. Thank you.
Thank you.
Very interesting. So, okay, we are perfectly in time. I don't see any question on the chat, so I suggest that what I propose is that there is any question, please unmute yourself and start asking. And so maybe I can start. Okay.
Sure. Thank you.
I have a couple of questions. One is a little bit naive, both are naive probably. So the first one, okay, I wonder if it is possible to use this device to produce a flow, in the sense without turbulence. If you put a large number of particles with a rotating magnetic field, each particle generates a small flow, no? Probably.
Yeah.
Do you think that is this sufficient to produce a kind of collective motion, a flow at scale much larger than the single particle? Do you think you can investigate this kind of problem? Or is it...
I think it's possible, but definitely not with these light particles. I think with if we can turn to some magnetic neutrally buoyant particles so that they can really suspended in the flow uniformly, and then we turn on the rotating magnetic field. Yeah, some flow will be generated. I also have read some literature about this kind of study. I think in Lyon, they people there are doing such research, just creating turbulence with magnetic particles, yeah, actuated by an external magnetic field. That's totally possible.
Yeah, no, indeed, it would kind of point vortices in 3 dimensions, no? And will be interesting. And okay, I have another very small, more technical question about your slide 10, if you can go back. So you mentioned, but I'm not sure I understand. So on the right, we see that there is a peak in the frequency, which is related to the frequency of the magnetic field, which increase, no?
Yes.
But at a certain point, this peak disappears. So it means that there is a maximum frequency that the particle can follow. This is the meaning, the interpretation. For 40 hertz, for example, or the yellow line,
Yeah, yeah.
the peak, you don't see the peak anymore. Or in any case, you see very, very small peak. What
There,
does
there,
it
there
mean?
could be multiple reasons why the at around 40 hertz vanished. Maybe because I don't have enough, statistics. Probably there is a very tiny peak there, but because the resolution is not good enough to see, or I would say because this series of PDFs is telling a story about how the turbulence dominated peak, which is in the middle, is
Yeah.
competing with the magnetism induced peak, which is shifting with the varying magnetic field frequency. The mechanism here is quite complex,
Yeah.
so it's hard to say where. Probably around 20 or 25 hertz. Here you can see at 25 hertz, the peak, the altitude of the magnetism peak starts to be lower than the turbulence generated peak. So this kind of from 20 to 25 hertz is where we usually say it's a kind of critical frequency somewhere that is related to the statistical average magnetism of the particle, the strength of the magnetic field, and also the intensity of the turbulence. Um, yeah, it's hard to have a conclusion about this exact number of the frequency.
Yeah, but it's very interesting, this point. Yeah, very nice.
Yes.
Thank you.
Yeah.
Thank you. So let's see if there is any other question. Okay, there is a question. Can you read the question? Is there an interaction
Yes.
between
So
the
it's
particles?
yeah,
No, is it-
it's a question from Lin Fu. Is
Yeah,
there any interaction between the particles? So because now in all the videos, in all the experiments we publish in this paper, we use volume fraction under 0.2%. So in this case, we basically say we can say there's barely no interaction between particles. It's still staying in the one-way coupling regime.
Yeah, because I asked
okay.
a good question because if we want to use, I do simulation. If we want to replicate your physics, so basically we basically need to know the interaction between particles. Otherwise, it will be a big problem
Yes.
for simulation. Yeah. Thanks
Yeah.
for your clarification. Yeah.
Yes. We intentionally try to keep this volume fraction lower than the threshold for between one-way and two-way couplings. Otherwise, because in this paper we just want to focus on algorithm to track the rotation of particle, which is only for the particle.
Yeah.
So yeah.
Okay, we have a question from Beverly, please.
Yes, thank you. Thank you for the talk. I wonder if you could just speak a little bit about the difficulty or lack thereof of doing the manufacture. So
The,
the
about particles?
spraying. Yeah.
Yeah, yeah.
Is it straightforward? Are there limitations? How big or small could you do this depending on the flow of interest?
That's a very good question. Thank you. I would say this is one of the biggest difficulties in the whole preparation for the setup to make such particles done because they have to be small enough to be comparable with the size of the Kolmogorov scale of the turbulence, which is decided by the size of the setup, and also they have to be light because we want those particles to go into the vortex filaments and they have to be magnetic enough to interact with the field. So about the fabrication, so as I mentioned, we just firstly need to buy some styrofoam particles from Amazon, from anything. It's quite common material. Uh, Originally, their diameter is around 500, 600 microns.
Mm.
So they're very light because styrofoam, their density is only like 0.05. It's only 1/20th of the water. And then I need to carefully grab those particles on a plate. On the plate, there is already some tape so that they can stick on the plate. And then I spray uh, after diluting the magnetic pin and to spray those magnetic pin on the particles with two different angles uniformly, slowly. And then I need to I think I need to wait for at least 2 hours to let the magnetic pin dry, and then I can get them out. That is how I make the particles.
Okay. Sounds like a very skilled procedure. So very good. Thank you.
And on that, so the final density is due to the magnetic paint.
Yes, the magnetic pin, the non-uniform magnetic pin, so that their magnetism is not uniform and they can have a
but also the final density of the particle, 0.2 is increased because of the magnetic paint with respect to
yes. The density, yes.
Okay.
Magnetic pin because it has a lot of magnetic dust in the pin, and I think their density is around 8.
Yeah.
So together, the general density of the particle is heavier.
Yeah. Thank you. So if there is any other question. Okay. There is a question from Michel Clotter. What is, sorry, I cannot read here. It's very small.
I can read the question.
Yeah.
So the question is, what is your depth of field for particles in focus to calculate 3D rotation? Yes, in this experiment, the depth of field that I define to have particles in focus, I think is around 4 millimeters. Yes, it's written in the paper. 4 millimeters. Yes. So the volume is like around 12 millimeters. It's a 12 millimeters cube, but only the 4 millimeter, this kind of thin slide in the middle, we have particles in focus because I have to put to have enough resolution on each single particle. I have to put camera quite close, and the field of view is quite small. So there is no way out to have a longer depth of field. That's quite a pity.
Yeah. Okay, there is another question by Michel. For particle diameters, the depth of field. So this limits the velocity. I think the maximal velocity to see the particle. No.
Sorry, the velocity.
This is Mike. Yeah. So the 4 particle diameters, your dt, the particle can't traverse more than 4 particle diameters in the depth direction.
I don't have a clear clue for that because I'm using a quite fast frame rate. I think I'm using around 3,000 frames per second. Basically, I don't think this is a big concern because before particles moving in this direction, in the direction of the depth of field, and then vanish in this getting blurry, most likely the particle will just get blocked by another one. And this is probably a 50-50, but my data efficiency is not very high, so that occasionally.
Okay, so you're going to see particles at reasonably high velocities that due to your high speed, your low delta t, I guess.
But
these particles will stay
still high enough.
Many of your particles will stay in field for many images. Thank you.
On average, every particle that is in focus stay in the volume for, let's say, around 40 frames on average.
Okay.
But
at some point, there would be a velocity limit, I suppose.
Yeah, of course.
So We have another very general question by Yang Yang. What is the application of this setup?
The application.
Maybe it's too early.
If you mean the application engineering, so far I would say we haven't thought about it. But of course, for our future research, we would like to study the very complex, rich interaction between particle and turbulence, because now we can really resolve their full dynamics, both translational and rotationally. So this is going to be a new field that hasn't been experimentally studied very well. And also because those particles are comparable with the Kolmogorov scale in our setup, this is definitely going into the details about the very basic structures about the turbulent particle-laden turbulence interactions.
Thank you.
So we have another more technical question by Stefan Schwett. How many pixels are approximately required per particle to do this work? So how many pixels you have for particles, the resolution?
Each single particle image has a resolution of 110 by 110. But if you say how many pixels are occupied by each particle, I would say the diameter of the particle in the image is around 80 pixels. Yes, because the particle size also varies a little bit in the sense of the pixel, the camera sense. The diameter also varies, I think, from maybe around 70 to around 90 pixels. So on average, 80 pixels, I would say.
Yeah, but the question probably is what is the minimum number of pixels you need in order to measure the rotation? No?
Yeah.
What's the lower limit exactly? So what is the lower limit? Do you have an idea?
Yes. We did this test with different pixels, different resolutions. So when the resolution goes down to 50% of what I'm using now, which is around 50, 40, 50 by 50, then the error bar is too large to accept. So I would recommend using at least 80 pixel by pixel, 80 by 80 pixels, sorry.
Okay, thank you.